rates, we are kind of almost past derivatives. You guys have seen and explored almost everything related to derivatives outside of the applications of derivatives. You've seen them applied to curves in terms of finding local max, local min, concavity, and things like that. But you haven't seen it applied to real world situations. And we have about four kind of lessons, so to speak, where we need to see it. One is called related rates. Another one is optimization, and you've seen already some of that last year. So that should be a little bit of review. Another one is something called economics. Are you familiar with this study?
No.
We did just a brief amount of economics earlier. And then finally, the last one is something just super fun called Newton's method. And then, one more, another mathematician, L'Hopital. L'Hopital came up with this really cool rule. And so we'll get some of that done before break, but we're not going to get it all done. So we'll come after break, we'll kind of wrap up those, and then move into our introduction to calculus 2, which is our integrals. And it's really it's a good ride. It is nice for everybody to kind of put derivatives to bed, so to speak. Okay, we've yep, your driver's license is currently at the printers. And it's being formatted right now, and so I'll show you. I kind of printed them off, but the ink quality wasn't really what I wanted. So like you can see, like is this? I don't have my glasses. Is this Bea?
Yeah.
But you see, like the ink quality is So I'm going to reprint them to make sure the ink quality is very high. I'm sure you guys are a little bit worried about that.
Yeah.
Just thinking the number of people that will look at it.
Right.
So.
Right.
So, and then they get double laminated and everything as well. So
Double?
yeah, double laminated. Yeah.
What is the reason for double?
Yeah. Well, that way they don't bend as much. They're more like
a
actual driver's license.
Why not triple?
Yeah. All right, here we go. Area of a circle increases at a rate of 20 square inches per minute. At what rate is the radius increasing when the radius is 5 inches? And that's what I love about this unit. Like when you look at it, it's like, what? We can make this problem so simple, so simple. And what I like to do is I like to first just, I divide this area up into 4 parts. I think that this is an excellent problem-solving graphic organizer. Where I usually diagram or I draw a picture here, okay? And then over here, I write some equations. Over here, I take my derivative. And here I solve. That's usually the process every single time, Okay, so kind of a picture diagramming situation. Get my equation. This is the toughest box to figure out. You guys get box 2, then you're all good to go. The rest of it's a piece of cake. So a circle, and it's getting bigger, right? So here's where we get to lean in together a little bit. If the circle's getting bigger, what aspects of the circle are changing? The diameter. What else? The radius. The circumference. The area, these are all changing, but they are all related to something else that's changing too.
Right.
Surface area, correct, but that would be in a 3-dimensional figure. We are 2-dimension here. There's something else that is kind of hidden up there in the problem that's also changing. Time. Time is the great variable that relates all these things, and they're changing together. Look at the rate is 20 inches squared per minute, okay? So per minute, so time is going by. So really, as I go ahead and I take the derivative, I'm not taking the derivative with respect to x, I'm taking the derivative with respect to time.
Okay.
I have this, a circle up here. It's got a radius. It's expanding. It's getting larger. I'm going to need an equation here for area. What is the formula for area of a circle? Pi r squared. That's one you're going to have to memorize. Okay. And I also like to write down some knowns and some unknowns here. It says the area of a circle increases at a rate. So this is the rate at which the area is increasing. So A prime is equal to 20. I'm wondering what R prime is. That's the question. I'm told that the current radius is 5. Now, this is where you have to be careful. I bring this up at different times, but right away people are like, well, if the radius is 5, just plug in 5 right away. You have to ask yourself, is the radius changing? Yes, if anything is changing, you can't plug it in right away. You have to wait until after you take the derivative. Everybody got that? Wait till after you take the derivative. So there's kind of like 4 level problems here. We're just dealing with level 1 today. We'll get some more difficult ones in the next couple days. But I want to take the derivative with respect to time of area equals pi r squared. And we're going to bring this back to a time where we took the derivative of, say, x squared plus y squared is equal to 36. Remember when we used implicit differentiation? And we said the derivative of x squared was 2x, and the derivative of y squared was 2y prime. Because if it didn't have an x, you attached a y prime, right? Is equal to 0. Everybody remember that? Well, now, if you look here, this is the derivative with respect to time. So if it doesn't have t as a variable, then we have to attach a prime to it. So the derivative of a is 1, but then we attach an a prime. Pi is a constant, but r squared, we would take the derivative, we would move the 2 in front, so 2 pi r, but r is not t, so we attach an r prime. Now we just solve. So a prime is 20. The current radius is 5. And r prime, we don't know. But we will be able to figure out now that we just plug those in. No big deal, right? So let's solve that. 20 is equal to 10 pi r prime. I will divide both sides by 10 pi. And I get r prime is equal to 2 over pi. And if I put that into a decimal form, I want to make sure I have a label, 2 divided by pi, and I get 0.636, or 0.636, and now we need to come up with a label. What unit of length will we use for this radius? Inches. Is it inches? Is it inches squared? Is it inches cubed? Inches squared is for area, but when you measure radius, radius is a single dimension, right? So it's just inches per minute.
I was congratulating you.
Not too bad? No, not at all. Look at another scenario that's very similar. A basketball is being filled with air at a rate of 1 cubic centimeter per second. At what rate is the radius increasing when the radius is 12 centimeters? So I like to diagram like this. I'm gonna, I don't know, does that help see as three-dimensional? Maybe?
Sure.
It's getting bigger. Here's a formula that you're going to need to know. Volume of a sphere is equal to 4/3 pi r cubed.
Learning anything every day.
And I will give you that formula on the test. Okay? There's a couple I will give you your way. Circle I will not. Okay, what do you know? What are some of your knowns? What are you given here?
We're given our
Yeah, the radius is 12. What else are we given?
increasing at a rate of 1.
And so what variable would that be?
Area prime.
Not
wait,
area prime, but
Oh, volume.
volume. This is a volume situation, isn't it?
Yeah.
V prime is equal to 1. At what rate is the radius increasing? I'm wondering what r is equal to. That is our unknown. I will take the derivative with respect to time. Of this shape, okay? So volume equals 4 over 3 pi r cubed. The derivative of volume with respect to time is v prime is equal to, I drop the 3 in front, and that just becomes 4 pi r squared r prime. So v prime is 1 equals 4 pi. What is the current radius? I can't see. 12. So 1 is equal to 12 squared is 144, and 144 times 4, is that 512?
It's like 576.
576, silly me. So I get 576 pi times r prime. We divide both sides by 576 pi. I get r prime is equal to, and I take 1 divided by parentheses 576 pi. Make sure that you put the pi in the parentheses, and it computes. Wow, it's a really small number, isn't it? So that's e to the negative 4, which means you have 3 zeros in front of that 5. So 0.0005 centimeters per second.
Okay.
Not too bad.
Not.
Okay, I think that there's just one more problem I want to do with you guys. And then I'm going to have you start working a little bit on your assignment here. And let's do example 3. It says, a right triangle has a base of 12 that remains constant while the height and area do increase. The area is increasing at a rate of 8 square centimeters per second. At what rate is the height increasing when the area is 64? Yep, I like that I put this problem together. This is a good problem. Again, a lot of these are what I refer to as just level 1 problems. We're just getting our feet wet with this. A right triangle. A base of 12 that remains constant. What does that mean? Right, so that's constant, whereas this gets larger and the area overall gets larger. Okay? So what formula should I write down? Area equals 1/2 base times height. Good. And what are some things that I know and what are some things I don't know?
The base.
Base is 12.
Don't know that.
We do not know the rate at which the height is increasing, and we don't know the current height either. Which one are we looking for, h prime or h? We're looking for h prime, okay? That's really what we're looking for. But we don't know h right now. What else? There's 2 more things I want to write up there.
Area prime is
A prime is 8, and area itself is equal to 64 at that time, right? See how in this situation, helpful to maybe list out a few things. Now, I'm trying to prepare you for what you're going to see, But right now, notice that here we have two different variables, don't we? And if you have two different variables and you're going to take the derivative, what rule would you have to use? The product rule. That's not very helpful in a lot of situations. We're going to go through some situations later on where we do use the product rule, and we're like, okay, that worked out well. But the reason why the product rule is not going to work out well here is because if you just think about it, you would get B prime H plus H prime B. Everybody agree? And notice we don't have B prime, do we? So we have no way of figuring that out. So that would not be helpful. But there is something here that helps us to be able to limit it to one variable, and that is this. Does the base ever change? No. So because it's constant, we can plug it in right away and get 6H. So that's the key to this problem, is understanding if it doesn't change, you can plug it in before you take the derivative. Everybody see that? All right, so we have the following. Derivative with respect to time is of A equals 6H. I have A prime equals 6H prime. So I'm going to solve. I have A prime is 8, and I have 6H prime. It turns out I don't even need to know that the area is 64, do I? Nor do I need to know what the current height is. If I wanted to figure out the current height, I could. I know that the current area is 64, set that equal to 6H, and I could figure out the current height. It is 64 over 6, or 32 over 3. I can figure that out, but I don't need it. I simply just divide both sides by 6, and I get 4 over 3, and our measurement in this situation is going to be centimeters per second for H prime. As you guys are working through these problems, you have the autonomy to be able to answer them however you want. I just want you to know that I have to be able to follow your work. I don't like it when math teachers say, you have to do it my way. I'm just trying to give you 4 boxes as a nice option. I did my master's work on this type of thing. I once taught a class where I went through this process and I didn't use the 4 boxes. And then I taught another class where I did use the 4 boxes. And I went ahead and tested them afterwards. And the class which was taught using this method, they tested higher. Okay, and that supports research that's out there all the time, that organizing your work in some fashion usually helps people work through these processes. So you do what you want, but if you look at your assignment, I simply just want you to work through problems 1 through 6, okay, 1 through 6. They work out quite nicely. I'm going to post the answer key right away. I would say before you leave the class today, you hopefully are able to do the very first 2 problems. The very first 2 problems. Okay?